right? Which one's better? NADH is way better. You produce more ATP from NADH than you do from FADH2.
FADH2?
Correct.
Okay.
So Dr. Tanner, in
Yes,
that
ma'am.
step with the GDP and the GTP, does that mean that the oxidation, or the oxidative phosphorylation and the substrate level phosphorylation is happening in that step?
They
Both?
do, yep. It's oxidative right here, and it's substrate level right here.
Okay.
Yep, well spotted. Okay, so the next stage is electron transport, right? And so what happens with electron transport? Now let's compare this for just a minute to photosynthesis. With electron transport, what we were doing is we were transferring electrons from a photosystem into the electron transport chain, right? And ultimately, for the electron transport chain that followed photosystem 2, that electron came from where? It came from photosystem 2, and there was a molecule,
The hydrogen.
P680, right? So P680 lost an electron up to the primary electron acceptor, and that was transferred over to the electron transport chain. But we don't have that here. So instead, what's transferring electrons over here to the electron transport chain? Yeah, all the electron carriers that we've made. So we're going to take NADH, and we're going to drop NADH off, or excuse me, we're going to drop an electron off on that topmost electron protein, and that protein's called a cytochrome protein, right? Now, this too is a redox reaction, right?
Yes.
What is being reduced? Yeah, the cytochrome protein in the electron transport chain, right? Because that's picking up the electron. And being oxidized is NADH, and it returns to NAD+. Okay. So that electron that gets dropped off here falls through the electron transport chain and ultimately out, right? And what's the purpose of an electron transport chain? To create a proton gradient, always and forever. So we're going to have protons over here. And these protons are going to be pumped out, right?
Mm-hmm.
So, question. What's this space below the membrane, and what's this space above the membrane? What's the space above the membrane, first of all?
Inner mitochondria.
It's in the mitochondrion. Where in the mitochondrion?
Inside the cell?
So there is some fluid for sure inside the mitochondria. Is it right here in the intermembrane space, or is it right here in the whole inner sanctum of the mitochondria?
In the inner sanctum.
It's close to the inner sanctum.
So in the
Intermembrane space, right? So this stuff up here, this is intermembrane space, and I'll write that so that we don't confuse that people. This is all intermembrane space. So what we're doing is we're creating a strong proton gradient in here, right? Okay, Carly, do you have a question?
I just want to make sure that I wrote this right.
Okay.
So I have it that it's kind of inside the inner membrane of the mitochondria. It's inside like that wall coming in between the inter and outer.
So the electron transport chain and the ATP synthase, they are embedded in the inner membrane.
Yeah.
And they're pumping stuff from the inner sanctum into the intermembrane space. And that stuff they're pumping, of course, is protons, hydrogen ions. You okay with that so far? Okay. All right, so we know that there's a strong proton gradient, and is that, creating that proton gradient, is that an active or a passive transport process? It's active, right? And it's active because it's requiring energy, and that energy is coming from what? The electron, exactly right. This is the energy. Which is kind of cool, right? Because ultimately that energy came from the complete oxidation of our glucose molecule. We've broken all of that up into electron energy, and we're using that electron energy to create this proton gradient. Now, the proton gradient is unhappy. It wants to diffuse back across the membrane, and the molecule that allows it to diffuse back across the membrane is ATP synthase, right? So these protons just fall back through ATP synthase. And when they fall through ATP synthase, it causes the molecule to do what?
To spin.
Spin. And that's kinetic energy. And that kinetic energy is used to create ATP. Exactly right. So what we're going to do is we're going to take a whole bunch of ADP plus some inorganic phosphates, and we're going to stick them all together using this kinetic energy to make a whole bunch of ATP. All right, and that's cellular respiration. So let's do our energy accounting. At each stage in cellular respiration, we've created something. And what are those things that we're creating? So glycolysis, what do we create in glycolysis? It makes some pyruvate.
NADH.
It makes an NADH.
And then ATP.
It makes an ATP. How many of each of those do we make? Pyruvate? 2. NADH?
2.
2. And ATP? Make 4, but we only get 2. Right? Perfect. And how much of that ATP did we make via oxidative phosphorylation? None. All of the ATP was made by substrate level phosphorylation. Okay, so Krebs cycle. What did we make in Krebs cycle?
ATP.
We made some ATP,
NADH.
made some CO2, NADH,
FADH.
and FADH2. How many ATPs did we make? 1 per cycle. CO2? 3 per cycle. NADH? 4. Where did we get our 4 from? So we have 1, 2, 3, and then over here, 4. And then how much FADH2 did we make? 1 per cycle, or 2 total. So why are we saying per cycle?
Because there's 2. Yeah.
And you guys have this. Because there are 2 pyruvates, right? And this turn of the Krebs cycle only shows one of the 2 pyruvates from our glucose molecule. So really it's double this, right? So for an entire glucose molecule, we make 2 ATPs, we make 6 carbon dioxides, which makes sense, right? Because we started off with 6 carbons in our glucose molecule and we completely digested that. NADHs, we end up making 8, and FADH2s, we end up making 2 of those for an entire glucose molecule. Does that difference make sense?
Mm-hmm.
This is for 1 pyruvate, which is half a glucose molecule, and this is for both pyruvates, or the complete glucose molecule. So at this stage in the Krebs cycle, how many of those 2 ATPs did we make via oxidative phosphorylation? 0, exactly right. This is substrate level phosphorylation, right? And it's that molecular magical kind of process where we're transferring phosphates between GTP and ADP. Okay, So here at the electron transport chain, what do we make? Proton gradient. That's all we're making here. And that's it, right? That's the entire purpose of the electron transport chain, is just to make that proton gradient. And then in chemiosmosis, we're making what? Making a bunch of ATP. How many do we make? 34 to 36, exactly right. Now, does this show us the complete picture of the electron transport chain? What are we missing? Okay, so here's where we get this like range idea being explained, right? Because FADH2 and NADH don't produce the same number of ATPs, and why not? Okay, so it drops it lower on the electron transport chain, right? So what we're saying is FADH2 is being reduced, or excuse me, being oxidized right here to FAD+, right? And what we know about potential energy is it's a product of state or position. And this really does represent potential energy. The higher up an electron is falling from, the more energy it represents. Here, that energy is really represented by the amount of protons that can be pumped across.
Why is it that it starts lower on the chain than, why couldn't it just like take NADH out of the way and start up higher?
That's a wonderful question, because the enzyme that catalyzes this oxidation reaction can't interact with that one. It can only interact with FADH2 and this one. Okay. So we know that FADH2 isn't as cool as NADH, right? But really, where does that range come from?
From inside, the inner membrane? With the...
Yeah, so it has something to do with the inner membrane, right? And this is getting back to Sophia's original idea. It's this bitty right here, right? This NADH. We don't know what to do with this, because this is in the intermembrane space, and we need it in the inner sanctum, inside the interior of the mitochondrion. But NADH can't move across this membrane. So what has to happen is it comes over here to the inner membrane, and it interacts with a protein that transfers that electron to either an NAD plus or an FAD plus inside the mitochondrion, right? And if it gets transferred to an NAD plus, we get another NADH, and we get 36 ATP. But if it gets transferred to an FADH2, then we get 34-ish ATPs.
So the NADH interacts with, what takes it from the inner membrane to out of it?
So NADH is going to come over here, and I didn't draw this last time, but I will this time, just for the sake of example. Holding the blue marker. So this NADH2, for example, could just come down here, and there is a protein embedded in this membrane that allows NADH to transfer its electron to there. So this gets reduced by NADH. And then what happens is either an NAD on the inside of the mitochondrion, all the way inside the inner membrane, or an FAD plus will come along here and get reduced to either FADH2 or NADH. So depending on which of those two electron carriers picks up that electron from this electron carrier, that's going to determine how many ATPs ultimately we receive. Okay? So total, oh yeah, go ahead.
So I just had a question about like the substrate level phosphorylation and the oxidative phosphorylation.
Okay.
So in glycolysis, all of that is substrate level phosphorylation, and then in all of the Krebs cycle, it's oxidative.
So it's to make ATP,
Yeah.
it's substrate level here and it's substrate level here.
Okay.
So substrate, the only place that we're making ATP with oxidative phosphorylation really is chemiosmosis.
Okay.
Good question. So total, how many electron carriers have we made through cellular respiration?
Wait, what? 18, can it,
4.
is it 40?
How many electron carriers
Oh,
have we made for all of cellular respiration?
The total of everything, 18.
For electron carriers? That's a really good estimate. Other ideas? How many electron carriers did we make here? 10. How many electron carriers did we make here? Here? How many did we make over here? 2. So that's a total of 12, right? How many NADHs total have we made? 10, right? 2 plus 8. So, from all of cellular respiration, total, how many ATPs can we make? 40. And how do we get 40? 36 plus 2, so that's 38. Plus how many over here? So how many we make, or is that how many we get? Yeah, so the total is 42, right? And how many can we gain? It's 40.
So,
We can make 42, but we gain 40.
so where do we get the 12 from again?
The 12 electron carriers. More than memorizing these statistics, you guys, really what I want you to be able to do is to look at this process and say, okay, so where did we actually make electron carriers, right? We made 10 electron carriers here at this stage. We made 2 down there. All right, so how would you guys like to see this on the exam come Wednesday?
How in depth?
So it won't be any more in depth than the stuff that we've gone over today, right? So please be familiar with, and I'll get out of the way so you guys can take a picture of this if you want. Please be familiar with like where redox reactions are occurring, what's being reduced, what's being oxidized. Certainly know the purpose of each stage. Certainly know the products of each stage.